Single-prompt AI models often fail when moved out of a sandbox and into a complex enterprise environment. They perform well in controlled demos, but they struggle to handle heavy, continuous production loads on their own. Achieving a reliable production environment requires the deterministic execution of multi-step workflows designed to function without human intervention. Reliability in these systems depends on a multiplexed array of specialized runtimes. Instead of relying on one monolithic language model to handle every logic gate, specialized units execute specific tasks. The design patterns of modern orchestration directly extend the 1970s Unix philosophy of modular, specialized computing. We are going to deconstruct this system by looking at the crystallized AI agent stack and the open standards currently governing it. Mastering this stack allows engineers to move past fragile single-prompt systems into the design of resilient enterprise architecture. The Unix philosophy dictates that software should be composed of small, highly specialized programs designed to do one thing well. This command shows modularity in action. Output feeds directly into the next program, passing data through distinct nodes. Early workflows were limited to single processes, but session multiplexing solves this. A master multiplexer node introduces a centralized control plane, monitoring multiple isolated processes simultaneously. Modern AI agent orchestrators, such as Claude Code, use this exact architectural parallel. The orchestrator functions as the control plane, replacing terminal sessions with isolated, specialized AI agents. While the structure is identical, the inputs differ. Instead of strict shell commands, the system routes natural language contexts and probabilistic reasoning. A master orchestrator spawns subagents, assigns them discrete pieces of a larger problem, and monitors their progress before assembling the final product. Agent orchestration is process multiplexing for language models. It forces probabilistic execution into a deterministic pipeline. The architecture of autonomous AI has converged into a four-layer stack: model, runtime, harness, and agent. The bottom layers, model and runtime, are infrastructure, handling raw token generation. But the harness layer is where the system is engineered, housing memory management and orchestration logic. The harness manages persistent memory, controls tool access, and directs the specific sequence of execution. To direct that execution, the harness routes tasks using three dominant orchestration topologies. In sequential pipelines, agents work in strict assembly line order, passing a data packet from one node to the next. Crew AI is the primary framework here, assigning distinct role labels to each node, ensuring every agent stays within its defined specialty. The second topology is graph-based conditional routing. Agents are nodes within a branching flowchart, where the execution path changes based on specific output conditions. LangGraph is the dominant framework for this approach, allowing for complex state management and compliance workflows. The third topology is conversational orchestration, primarily utilized by Microsoft AutoGen. Here, agents iteratively refine outputs through simulated dialogue. Choosing the correct topology within the harness layer determines whether a problem is solved efficiently or spirals into unmanageable context errors. Without the ability to read and write to external systems, an AI agent is isolated. It has no way to interact with the databases or tools required for real work. Historically, connecting agents to proprietary data required engineers to build custom API integrations for every individual model. An API, or Application Programming Interface, is a set of rules that allows different software applications to communicate with each other. In 2025, the Agentic AI Foundation addressed this with the Model Context Protocol, or MCP. It acts as a standardized intermediary. Using a lightweight JSON RPC 2.0 connection, it serves as a universal serial bus for AI, allowing models to be swapped without rebuilding data connections. This standard has seen massive adoption, with thousands of published servers and millions of monthly SDK downloads. An SDK, or Software Development Kit, is a collection of tools that allows developers to create software for a specific platform. By building a single MCP server, developers grant immediate read and execute access to any compatible orchestration system. This is supported by the agents.md standard, a markdown file that provides repository-specific instructions directly to an agent's context. These standards enable local-first frameworks like Block's Goose to run autonomous tool-calling operations entirely on local hardware. While efficient, granting models this level of access requires strict security measures. Engineers must mitigate risks like prompt injection, where a malicious input forces the agent to immediately execute highly unauthorized commands. Open standards like MCP shift AI from an isolated chat interface into a fully integrated system actor. Autonomous orchestration has shifted the economic baseline of software development. PR merge rates for autonomous agents are now hitting levels that fundamentally change project timelines. A PR, or pull request, is a request to merge new code changes into a main project. Raw code generation speed is no longer the primary constraint in development. Efficiency now depends on the quality of problem definition and the clarity of architectural boundaries. This has created new disciplines for the engineer: context engineering and the development of secure MCP servers. The manual writing of syntax loops is being replaced by the technical definition of boundaries for autonomous systems. Engineering teams should use a build versus buy evaluation for orchestration, avoiding custom harnesses unless a specific business logic requires it. For standard refactoring and development tasks, pre-packaged harnesses like Claude Code or Aider provide the most efficient path. Custom graph orchestration is best reserved for proprietary business workflows where precise state tracking is mandatory. The functional distinction between the terminal and the IDE is eroding as agents operate seamlessly across both interfaces. This shifts the role of the engineer. The machine handles the low-level syntax. The human responsibility is now the technical definition of the system's boundaries, the harness, the protocols, and the specific intent that governs autonomous execution.